I think we can get started with this plenary session of the energy frontier. Alessandro will give a brief introduction to the two talks that we have planned for this afternoon, one on Higgs factories and the other one on multi-TeV colliders. There will be no questions after Alessandro's brief introduction, but then we have questions after each talk. Just urgent ones, because we want to reserve a time at the end for discussion and Q&A. So the floor is yours. And there is, of course, a document attached to this presentation where you can start typing your questions for the final discussion.
Hello, can you hear me? Is it good? Okay, nobody's complaining. Okay. Welcome to the Energy Frontier plenary session. I'm very pleased to present the two speakers, Sally Dawson and Simone Pagani-Griso, who will follow my brief introduction. Before this, I want to highlight the fact that we have a second version of topic group reports and Energy Frontier report available and publicly available to you for commenting. So just go to this wiki page and you will find the report as well as a Google document where you can enter your comments, suggestions, or complaints. But before I start, I would like to ask the topic group conveners of the Energy Frontier to stand up, those who are in the room, and I would like to thank them. Please stand up, those who are present. It's not an overstatement to say those are the pillars of the Energy Frontier. Without them, we could not be where we are. And of course, all the mistakes are from the three of us, Nashi, Laura, and me. But the great amount of work that's done is all merit of the topic group conveners. So thank you again. And let's start with the goals of the Energy Frontier. We want to address big questions. And the big questions are listed here: the evolution of the early universe, understand the matter-antimatter asymmetry, the nature of dark matter, the origin of neutrino mass, the origin of electroweak scale, origin of flavor. Okay, well, you see these big questions also are closely related to big questions in other frontiers. So really, we thrive on the cross-frontier fertilization. So we try to tackle same questions from different points of view. But also we want to explore the unknown. Exploring the unknown has been a driving force in discoveries at the Energy Frontier, and we believe will remain so in the next decades. And in order to discover for new physics beyond the standard model, we follow a two-tier approach. We want to study known phenomena with the highest possible precision, and also search for direct evidence of physics beyond the standard model. And any new discovery at the Energy Frontier really relies on new accelerator and new detector technologies, as well as advances in theory, and also advances in analysis technologies and methodologies. So we require substantial resources and R&D in several sectors in order to enable our research at the Energy Frontier. And we live in a very peculiar time in which we don't have a clear guidance from the theory of what will be the next, the scale of the next physics beyond the standard model. We have to rely on experimental guidance. So it's our duty to plan for the next experiments at the Energy Frontier. The most immediate project, which is highly awaited but also approved as a short-term project, is the high luminosity LHC. This is a critical project for the Energy Frontier. But I have to prepare for a bit intermediate and longer-term projects at the Energy Frontier, and we believe Higgs factories and multi-TeV colliders are the next steps that enable discoveries at the Energy Frontier. And what we are doing here, what we've been doing some for the last 2 years, and we are doing here, is to try to identify a path forward towards the next accelerators and next machines and experiments beyond the high luminosity LHC. And we do not know exactly where the new physics is. It could be at low energy scales as well as high energy scales. Naturalness seems to indicate that new physics is close to the electroweak scales, but also direct constraints have put quite tight bounds around 1 to 2 TeV. And the methodology that we can employ to discover new physics really depends on the type of new physics we're looking at, what type of energy, what scale of energy we want to reach, and we can reach, and also what type of colliders we can and we want to build. So, and I want to illustrate here something which may appear as a dichotomy, precision versus energy reach. But hopefully I will convince you that it's not dichotomy, is really complementarity. In this scheme, if you put the mass scale on one axis and the coupling of BSM to standard model, the LHC is roughly here in the middle. With Higgs factories, you can reach kinematic phase space that are not accessible by the LHC or high luminosity LHC, mostly low values of couplings. And here we need high luminosity, high statistics. But also with high energy colliders, we can reach high mass scales. And these really, as you see, cover complementary regions of phase space. So we need both precision and energy reach for the next colliders. And the discovery of Higgs bosons has been critical for our field. We celebrated the 10th anniversary just a couple of weeks ago. And although it seems to be completing the standard model, it's also a portal for new physics. It's a very peculiar particle with peculiar properties we've never seen before. And fundamental question is whether this particle is fundamental, composite, and how it interacts with the physics beyond the standard model. So in the talk by Sally, there will be a motivation why is it so important to understand the nature of the Higgs boson. But also we need to explore physics beyond the standard model, directly and indirectly. And for this, we need not only Higgs factories, but also the next generation of machines at the multi-TV scale. And Simone Pagangriso will illustrate and motivate the need for multi-TV colliders. So with this, I conclude this brief introduction, and I invite Sally to motivate the need for Higgs factories.
Okay, so it's indeed a pleasure to be here at Snowmass in person after so much time at home. And I've been asked to talk about the case for precision Higgs physics. Why is it that we spend so much time thinking about the Higgs, and why do we have these proposals to build high energy E+ E- colliders to study Higgs physics? Of course, the energy frontier is a very broad frontier. It covers many different kinds of physics. So I'm just going to give you a snapshot of why the Higgs is so central to our vision. Maybe. Go down the other. Okay, so the landscape in particle physics has changed dramatically since the discovery in 2012. Before 2012, the Higgs might not have existed. It could have been very heavy. So it completely changed the way we think about physics. But in the last 10 years, we have turned from discovery science of the Higgs to the precision program. So when I talk about a Higgs precision program, I'm talking about high Lumi LHC, followed by E+ E- colliders, and maybe followed by muon colliders. So we are already in the age of precision physics. And of course, you can see it by looking at any set of plots from the LHC, going from discovery in 2012 to measurements in 2022. They get much more precise and the number of events gets much larger. So we are now in the era of precision physics. And when we study Higgs couplings, it's very useful to quantify them as their relationship to the standard model values. And we call this the so-called Kappa scheme. So we normalize all of our measurements to the predictions in the standard model. And right now we have the Higgs couplings to fermions and gauge bosons at roughly the 5 to 10% accuracy level. And I like this plot from CMS that they had for the 10th anniversary, because what they show here is the evolution and precision of various couplings. Say here's the W, the Z, and they show how they evolved with time from discovery to run 1 to right now, and then a prediction for the high LUMI LHC. So you can see the march in precision over the last decade and the predictions for the future. So we've really seen with the high LUMI or with the LHC measurements so far, the triumph of the standard model. We have these precise calculations of Higgs boson quantities, and we're able to compare them precisely with Higgs production at the LHC. And this kind of reminds you of the LET program, where you had precise calculations, precise measurements, and you could really nail down the standard model. And that's what we're doing right now. So this theory program, I think it's important to note that this wasn't just turning the crank, it's really developing new tools for these Higgs calculations, these incredibly precise predictions, and using the standard model as a benchmark. And you can see just over here on the right, the progression of our theory predictions, green, blue, red, and here is the Atlas Higgs to gamma measurement. So we're really making precise measurements, precise predictions for Higgs properties. And for the future, it's all about comparing these very precise measurements with these very precise calculations. So it's all about understanding the uncertainties, both theoretical and experimental. And you can see the projections here for the high LUMI LHC. This was from the European Strategy Report. It has not been updated since then, but you can see theory is the red, statistical is the blue, and the middle one, the green, is experimental. And they all contribute, and the projections are for measurements in the few percentage level, 2 to 4% in the high LUMI LHC. So this will be the first step in our precision program, going from the 5 to 10% accuracy we have now to the few percent accuracy in the future. But despite all this beautiful and immense progress, our understanding is incomplete, and we're really just at the tip of the iceberg of Higgs physics. We're only beginning the study of what's going on in electroweak symmetry breaking and what's going on with the Higgs. We have these 5 to 10% measurements of the top quark, the bottom quark, the W and the Z interactions with the Higgs. We have a 0.1% measurement of the Higgs mass. We know that the Higgs is spin 0, but there's so much we don't know. There's so many important questions that we still have to address. We don't know anything about the couplings to the first generation, up, down, and electron. We don't know anything about the couplings to the second generation, strange, charm, and mu. We don't know very much about the Higgs self-couplings, flavor violating Higgs couplings. We don't know anything at all about that. We don't know if the Higgs has any CP violating interactions, but we have ideas for exploring all of these things at future colliders. For example, the coupling of the Higgs to the muon is expected to be nailed down with 400 inverse femtobarns at the LHC, and the full run of the high LUMI LHC will give us a precision measurement of the Higgs couplings to muons. The couplings to charm quarks remain very difficult at the high LUMI LHC, but I'm hopeful that we'll eventually figure out a new way to do this. Right now, we're within about a factor of 3 of the standard model. The couplings to strange quarks, we've heard during this meeting that there have been very clever ideas about strange tagging that would be relevant at a high energy E plus E minus collider. So we expect to make progress here. The Higgs self-couplings, there's been a tremendous amount of work about the possibilities at the high LUMI LHC and about future E plus E minus colliders. And we can see a path where our knowledge increases as we go through these various options in the future. So we know there must be new physics. We have these whole host of questions that we hear about in every talk, in every colloquium: dark matter, the matter-antimatter asymmetry. We don't understand why the top quark is heavy and the neutrino is light. We don't understand why the W and the Higgs are so much lighter than the Planck scale. We don't understand why there's only one doublet in the standard model. But many of these questions can be answered with Higgs physics. When theorists try to think about how we can understand dark matter or how we can understand the pattern of fermion masses, we inevitably construct models and scenarios that involve measurements in the Higgs sector. So we're in this new paradigm. Before, Before the Higgs discovery, we knew that the Higgs had to be sort of less than about 800 GeV, or perturbative unitarity would be violated because our cross sections would grow with energy. And this led to this powerful, powerful idea of a no-lose theorem at the LHC, that the LHC had to find a Higgs or there'd be something else. And unfortunately, today, we do not have this no-lose theorem. We don't know where the new physics might be. So the energy frontier has a broad search program. We have to look broadly for where this new physics might be. So in exploring the Higgs sector, there are two complementary ways to go about it. We can measure Higgs properties very, very precisely. And the goal is to compare the Higgs properties we measure with the standard model predictions as accurately as possible. And of course, it's a real triumph to be able to have the experimental measurements and the theory and really pin down the standard model. So measuring the standard model is a discovery if we can do this. Measuring not the standard model is also a discovery. So these Higgs coupling measurements are win-win. No matter what you measure, you're learning something about the universe. The other way to probe the Higgs sector is to look for more Higgs-like particles. And this is primarily the realm of the high LUMI LHC, where they'll extend our current sensitivity. So the lepton colliders offer new opportunities going beyond the discoveries expected at the high LUMI LHC. So what I've shown here is just the rate for making the Higgs plus anything as a function of the collider energy. So the yellow curve here, you see it's got a bump and a dip. This is E plus E minus goes to Z plus Higgs, which is shown right here. So you can see that if you run sort of right above this peak, 240 or so, you really get the maximum cross section. So all of the proposals for new E plus E minus colliders have a scenario where they run right here. Then they have E plus E minus goes to Z plus Higgs. So using missing mass techniques, conservation of energy, they can tag the Higgs boson and get very, very precise Higgs couplings. As the machines evolve to higher energies, you start to see this red curve here, which is the WW going to Higgs. So you can measure the couplings of the W's, the interactions of the W's with the Higgs very precisely. And putting these two together gives you a very strong result on the Higgs couplings. So there are many, many opportunities here. I listed the ones here that the energy frontier studied. And I want to point out that all of these have a run at 240. So here we go. Here's 380. 250. So this is running at the ZH maximum cross section for the first set of runs. And then you can see the linear colliders, ILC and CLIC, go up to higher energies, 500 GeV and 1 TeV, where you get the TTH coupling and rather precise measurements of the HH interactions. The circular colliders, CEPC and FCCEE, can run on the Z pole and then on the 2W threshold to have a very rich program of precision electron weak measurements. And so here I'm focusing on Higgs measurements, but I'd be remiss not to make the point that these colliders have a wide range of very important physics results. If you run at the Z pole, you will have extremely precise measurements of standard model quantities. WW measurements probe the structure of the SU2U1 gauge theories. They have a QCD program. So there's a whole host of things other than Higgs physics at these machines. So I'm often asked when I talk about the Higgs, well, how precisely do you have to measure the Higgs coupling? And this is a really important question. And the only way I know to answer this question is to think about various models that theorists construct and ask the question of what kind of scales do they probe? Well, naively, the deviations and couplings are sort of V squared over lambda squared, where V is 246 GeV and lambda is some TeV scale. So if you make a 1.5% measurement, you're sort of probing the 2 TeV energy scale. And you can go through your favorite models. I've listed some here, and you get deviations on the percentage level. So for example, extra Higgs doublets, you get deviations on the sub% level. Composite Higgs models tend to get deviations on the few percent level. So the idea is that when we make these measurements, we'll nail down the standard model, or we'll see some pattern of deviations. And it's the pattern of deviation which will give you a hint as to what the underlying physics is. So you can compare all the machines and ask, well, how well do they measure these couplings? How well do they probe them? And again, it's a stringent test of the standard model because these are absolute predictions. In the standard model, there's no fudge factor. They're absolute predictions. And so, as I've said, they're typically sensitive to new physics at the 1 to 2 TeV scale. So these future colliders offer the opportunities to improve our knowledge significantly. So here's the precision on couplings for various couplings. Note that this is a logarithmic scale, and these are different channels, the couplings to Z's, to B's, to photons, and so forth and so on. And the gray is a high Lumi LHC, so you can see it's the few percent level. Here's a couple percent. So it's a few percent level. So we're going from now the 5 to 10% level at the high Lumi LHC to the 2 to 5% level. And then at the E plus E minus colliders, we're going to the percent level. So this is the evolution in our knowledge of these interactions. So you can ask the question, why should there be only one Higgs boson? We could just as easily have had a pattern of 2 or 3 Higgs doublets. It's just as natural to do this. And so the simplest case that I can look at is to say, well, maybe there are 2 Higgs doublets. And this is a good test case for understanding, looking for new Higgs physics. So you can measure Higgs coupling measurements. In these models, they're characterized by a mass scale of the second Higgs scalar and by a ratio of vacuum expectation values. And these two plots have the same scale. So it's the mass of the heavy guy on the x-axis and this tan beta, the ratio of BEVs on the y-axis. And these are both studies that were done for the snow mass process. And you can see this kind of nose-like shape of cutting out parameter space going from the LHC to the high Lumi LHC, which is the yellow, and then the E plus E minus machines getting ever more precise. And on the other hand, the direct search at the high Lumi LHC cuts out this blue region, which is sort of complementary to this region. So the picture is that you put both together and you get more information about your model. So now we come to what's really one of the main motivations for future Higgs physics, and that's the study of the Higgs potential. We have this whole beautiful electroweak theory where the W and the Z get their mass through electroweak symmetry breaking, coupling to the Higgs doublet, which is broken through a VEV. But there's absolutely no experimental evidence that this is the case. In order to pin down how this electroweak symmetry breaking happens, you have to measure the parameters in the Higgs potential. So in the Higgs potential, we've got the Higgs mass squared, but we've got the Higgs cubic interactions and the Higgs quartic interactions. And the coefficients of these are absolute predictions of the standard model. So we need to measure these to see if we really have this beautiful electroweak symmetry breaking that we think we do. So we can probe this interaction through double Higgs production or through loop corrections to single Higgs production. And you can probe this one through triple Higgs production. And the triple Higgs production has an excruciatingly small rate, and we can't do it at the future E plus E minus colliders, but there is some possibility that we might be able to do this at a 100 TeV machine or a high energy muon collider. This cubic interaction is going to be probed at the high Lumi LHC and then further at future E plus E minus machines. So double Higgs production has received a lot of attention in the context of the high Lumi LHC, and it's sensitive to the self interactions of the Higgs through diagrams like this. And then there are other contributions which don't depend on the self interaction of the Higgs. And there's been a tremendous amount of progress in understanding how this works, both theoretically and experimentally in terms of projections. And I have to point out that the current run 2 results exceed the projections that were made a decade ago. So the experiments are really doing much, much better than what we projected. So for snow mass, there was an update from Atlas where they studied 2 channels and optimized them. CMS updated some of their channels, but the pieces have not yet been put together to have an official projection for how well they can do at the high Lumi LHC. So at the Higgs birthday party at CERN, Liza Brott said, well, back of the envelope says it's going to be 5 sigma when you put them together. So as a theorist, I can say it, I'm hoping for 5 sigma with the full 3 inverse Autobarn program. So this is something that will come in the future, putting this together. So once we've observed double Higgs production, we of course want to extract the parameters of the Higgs potential. This is really a very important goal of the future program because it depends on our understanding of electroweak symmetry breaking. And again, it would be a triumph of the standard model if we could really nail down what it was. And it's also extremely sensitive to new physics, to new resonances. Anything that happens in BSM models tends to change the double Higgs rate. So here I just show the precision on the HHH coupling, a 50% measurement with the full run of the high LUMI LHC. And then if you go to the FCC, HH, or muon collider, you get down here to the sub 5% level. But I want to emphasize that these measurements are all extremely interesting because it's not hard to have a model where the change is much, much bigger than this. For example, in my favorite 2 Higgs doublet model, you get enhancements of the double Higgs rate by sort of factors of 2. So here's 0 is the standard model limit, and the greenish here is a region where the double Higgs rate is twice as big as it is in the standard model. So the future colliders are sensitive to this enhancement of the rate. So this is within our grasp, seeing these kinds of effects. So one of the reasons we expect new physics in the Higgs sector is the naturalness argument, which Alexander alluded to. And it's because having light fundamental scalars really raises theoretical issues. If we calculate quantum corrections to scalar masses, they tend to give corrections which are proportional to the mass of the new physics squared. So in general, new physics that interacts with the Higgs boson tends to have large effects, m squared nu. So these kinds of scalars would change the Higgs width. So why does the Higgs width matter? Well, first of all, in the standard model, it's absolutely predicted. It's 4 MeV. The uncertainty on the prediction is quite small. The Higgs width is sensitive to new particles that might come in to answer this naturalness problem. So again, we might expect that they would change the Higgs width. And the future lepton colliders, one of their real strengths is that they give extremely precise and rather model independent measurements of the width, which is a probe both of the standard model and of new physics, which would address the naturalness problem. So here is just the measurements of the width. So there's a measurement at the high LUMI LHC, which is about 17%, and then the measurements at the E+ E- colliders. And I have to say that these measurements rely on quite different theoretical assumptions, but it's very impressive that we think we're going to start to have a measurement of the Higgs width, because when people started thinking about this 2 decades ago, it was impossible. We just never thought that this could be done. So the Higgs width is also sensitive to these new particles in loops. This is an example from a SUSY model. So this is an example with scalar partners of the top quark showing the improvement as you go from the LHC high LUMI, which is the red, up to CEPC plus E minus FCC EHH. So again, as you have your progression of these E+ E- colliders, you start to really probe new phase space and new interactions. So Higgs and flavor, they're the anomalies in B physics, and they suggest that maybe something is going on with flavor. Now, in the standard model, all the Higgs couplings are flavor diagonal, but there's no particular reason why this has to be true. In more complicated models, you can certainly construct cases where the Higgs couplings are not diagonal in flavor space. So for example, this is an example where the Higgs coupling to strange quarks is enhanced in a flavor violating 2HGM. So this is the 125 GeV Higgs couplings to strange quarks normalized to the standard model. And again, you can see the progression of our knowledge from high LUMI LHC to the E+ E- colliders. And this results from a nice white paper that came to the energy frontier on strange tagging at the ILC. So the high LUMI LHC future E+ E- colliders can probe the flavor violation in the Higgs sector. The Higgs could be a portal to dark matter. Simple models, the Higgs couples light dark matter scalar. This kind of simple model can explain the baryon anti-baryon asymmetry, changes the Higgs couplings to standard model particles. Again, you can see the sensitivity of the various machines. So here's my light dark matter scalar, and here's my branching ratio of the standard model Higgs to this dark matter scalar. And the light gray here, I guess it's brown, is the region where you get a first order electroweak phase transition, and so can explain this baryon anti-baryon asymmetry. And again, you can see the high Lumi LHC followed by the Higgs factor results, improving our knowledge. My last physics example is CP violation. So Andre Gritzen invented a new kind of Feynman diagram for us in this workshop. And so the baseballs can be either quarks or leptons. And so our future colliders have the capability to probe whether the Higgs has a little bit of CP violation. And of course, this is something we don't understand, and it would be great to understand. The high Lumi LHC can get, for example, the top Higgs CP violating couplings. The future lepton colliders, along with the high Lumi LHC, can look for CP violation in the Higgs couplings to Z and to photons, and is complementary to the measurements in electron EDMs, which I think is a nice connection of the energy frontier and Higgs physics to the other frontiers. So I just want to flash this to go back and remind us all that these Higgs factories, they do these beautiful, exciting Higgs measurements, but they also have this rich program beyond the Higgs in the E+E- machines. They can do BSM searches. This is a search for heavy neutral leptons. They can do precision electroweak anomalous gauge couplings, precision measurements of standard model quantities. So it's a physics program with any number of physics results. And of course, the Higgs, much as we know and love it, it's connected to the whole standard model. We know that the standard model is an excellent low energy effective field theory, but in the effective field theory way of thinking about things, interactions of the Higgs are connected to interactions of the top, which are connected to WW interactions, which are connected to Z-pole interactions. So all of these measurements are connected. So by measuring, for example, top quark at high Lumi LHC, we can connect it to Higgs measurements and probe the Yukawa structure of the standard model. Similarly, future Z-pole and diboson measurements are connected to the Higgs measurements within this context of effective field theory. And it's important to note that these effective field theory approaches don't assume very much. They assume that the Higgs is an SU2 doublet, but beyond that, they're pretty model independent. So in the effective field theory framework, what really happens is that the E+E- machines really nail down the coupling of the Higgs to the Z, gets much more precise. So let me just conclude by saying that there are many, many questions that can be answered by measurements at Higgs factories, where we have within our capability test of the standard model at the 1% level, and this future Higgs program can address many of these fundamental questions of particle physics. Is there an extended Higgs sector? Why is there dark matter? What about flavor? So we have a way of addressing these questions. So let me just end with the energy frontier vision in the Higgs sector. I think we've made the case that the physics case for exploring the Higgs and the electroweak symmetry breaking is compelling. I don't know if that's the right word. I should maybe use crucial or foremost important. And the full run of the high Lumi LHC is going to make major advances in our understanding of the Higgs. And the next step in the understanding is going to come from the future E+E- machines, which will give us significant gains in precision in our understanding of electroweak symmetry breaking. And these machines have a lot of measurements, searches, discoveries, a path with physics results and opportunities for students going forward. And part of the energy frontier vision is to endorse lots of R&D to figure out how we can go forward with a high energy muon collider or 100 TeV collider. Thank you. I'll stop there.
Thank you, Sally, for this beautiful talk. We have a little bit of time for questions, urgent questions, and then I remind you there will be a discussion at the end. Julia, one or two questions? I don't see any.
Thank you very much for the really nice talk. What would happen to the future of dark matter picture if you don't find any deviation on the Higgs factories or the Higgs properties?
Your question is, what is the implication if we don't find any deviations?
Yeah, in the
For
dark,
dark
matter.
matter. Well, interpreting the Higgs as connected to dark matter is very dependent on model construction. There are a lot of models for Higgs and dark matter. So I think if we didn't find anything in the context of this particular model, that there's a whole range of studies, which I think Zen talked about in the BSM talk this morning. So there are many possibilities.
Okay, not seeing any other raised hand. I think we can, thanks, Sally, again. I invite Simone Pagangriso for our next talk on multi-TV colliders.
Okay. So, well, first of all, let me say that it's really, really nice to be here in front of a live audience and to give a talk on a topic that I'm really passionate about. So thank you everybody for coming. And when I started preparing this talk, I thought that sort of, given that the topics is sort of on the planning and forward looking, the first thing we should look is actually the past and see sort of what has taught us. And so that's why sort of the first picture is a picture you've seen all many times this week, is about the standard model of particle physics. And what I wanted to highlight is how colliders have been instrumental to really build our knowledge of the standard model. And here I've highlighted sort of many of the discoveries that Collider have done through an experimental program that lasted more than 50 years and brought us here. But this, we know that is not enough, but it can teach us quite a few things. And there are two themes in particular that I wanted to highlight because they are coming also very strong in our planning for the future. And these two key elements are the interplay of theory and experiment, as well as the interplay between direct searches and precision or indirect searches, if you want, of physics beyond the standard model. And there are several examples of the success of these interplays. I just wanted to briefly mention one, which is the when we look essentially for indirect effect of the Higgs boson into precision standard model observables. And this has been done long before the Higgs boson was discovered, and that allowed us to pinpoint what mass range the Higgs boson could have been lying. And you can see how this plot sort of evolves versus time. This is sort of a chi-square versus the Higgs mass. And back in 1996, and then in 2005, how it gets narrowed through precision measurements, while the yellow band points to the direct searches that sort of were not finding any evidence of the Higgs. And then finally in March 2012, just before the discovery. And then finally, just in July 2012, just turned 10 years ago to this month, we had finally the Higgs discovery. And I think this is just one example that really highlights both of these concepts very nicely. And as I said, both of these concepts are actually quite featured also in our plan looking forward. But standard model is not enough. We know that. And Alessandro has already illustrated and read to you some of the fundamental questions that we decided to put certainly in the spotlight for our plan looking forward. And the truth is that there are plenty of extensions of the standard model that can explain these questions. And these plots sort of nicely illustrate the sort of these big questions map into different ideas. And in addition to sort of the ideas we thought about, there is this last row that illustrated that also there can be new ideas coming up from here looking forward. And most of these extension point to new particles that will manifest at higher energy scales. With such an exciting and vast set of possibilities, what I think is really imperative is really having a broad physics program. And this is illustrated by sort of this expansion of this figure, which shows how this question connects to various sectors of the standard models. And then each sector of the standard model can be probed in various different ways. And in that sense, Collider really offer a unique opportunity because in a single experimental setup, they can probe all these sectors of the standard models. And that's a pretty unique feature of the Collider program. And so let me just spend one slide on our current energy frontier collider, which is the Large Hadron Collider, which has just started taking data in what is called the run tree. This again happened this month, busy month. You can see it here. This is basically beginning of July. And the run tree has started, and this was sort of the first 13.6 TeV collision of the run tree. This is just a screenshot of the point one with the various beams and the energy. But so how do we go beyond LHC? You've seen this figure, and this has been already illustrated. So we can go down in coupling of precision, and we can go higher in mass scales. And the purpose of this talk is to illustrate you how do we plan to push further in the higher energy scale or mass scales. And let me start to say that actually our next energy frontier collider is actually coming up pretty soon, and it's the high luminosity LHC. And the reason for that is that so far the LHC program has delivered about 5% of the total luminosity that we expect from the LHC plus high luminosity LHC program. So why is that important for the energy scale? And it's because only a fraction of the proton-proton interaction, the center of mass energy of the interaction is transferred to the Hard scattering interaction. That practically means that you need a large number of interactions, so a large luminosity to probe higher energy scale. And I think this is nicely illustrated by this projection, which shows for just an example of a sort of a higher mass mediator Z prime, this is a limit on the cross section as function of the mass of the mediator. And this painter band sort of shows the limit in the cross section that you expect versus mass from the current measurement of run 2. And this is what you expect after the high luminosity LHC. The solid lines are the theory prediction for a Z prime, for such a high scale mediator as function of its mass. And so the intersection of these two curves shows essentially the energy scale we are sensitive to. So you can see that moving to lower cross section, so having higher luminosity, practically means that we are sensitive to higher energy scales. And I don't have time to go into details, but the high luminosity program is actually even much more, and there are many ideas to extend it even further. So how do we go beyond even high luminosity? And there are essentially, I would say, three main things that I would like to discuss briefly. And we can use proton-proton colliders to go to higher center of mass energy, E plus, E minus, or mu plus, mu minus. There are also options for lepton-hadron colliders, which are very interesting. They have synergy with proton-proton as well as discovery potential by their own, but I will not touch them in this presentation. But let me start for proton-proton. So if you want to go to higher energy than what LHC does, what you need is a larger ring and stronger magnets. And the reason for that is really just in this simple format, where the momentum of the beam is essentially, you need to keep the beam in the ring, so it depends on the radius of the ring and the strength of the magnetic field to keep it inside. As easy as that. Then the second thing, you need larger statistics, so larger luminosity, exactly for the reason I illustrated before, the example of Z prime. And we have sort of two main proposals I will focus on. They're called FCCHH and SPPC. They both foresee a ring, a new collider ring, which is of the order of 100 kilometers, and they aim to reach center of mass energy of around 100 TeV. An alternative is try to push on E plus E minus collision. Here, the main problem is that if you try to do a bigger ring, you run into a huge problem with sort of power loss due to synchrotron radiation, which depends on the Lorentz factor of the 4th power. So this is really a barrier. So the only way to go to very high energies is essentially go to a linear collider. This means that you need a larger accelerator gradient, but it pays off because you have low physics background and a much easier event reconstruction. So here you see two sort of classes of proposal for a linear collider around 3 TeV, and then moving it further in the future, colliders up to 15 TeV. So in this situation, especially actually a photon-photon collider is technically preferred, but the physics studies for that is a bit less studied. Finally, we had actually a lot of interest in this NOMAS round about the possibility of a mu plus mu minus collider. Just to give you a feeling of how big this interest was, we received more than 40 contributed papers in the energy frontier. It's about a third of the total. And a muon collider forum was set up, and the report of that is signed by more than 60 early career authors out of, let's say, it's about 50% of the authors. So there is a large interest by the young community. And this is extremely interesting because you can see down here the sort of the type of proposal we've been focusing on a 3 and 10 TeV collider. It can be realized in a pretty compact collider ring of 5 or 10 kilometers, but has challenges because, as a reminder, the muon lifetime at rest is about 2 microseconds. So you need to be very fast to accelerate muons and bring them to collision. And this means that while you do them, some of them will decay, creating a large beam-induced background. But again, the reward is that you have very low physics background, and in principle, such idea is scalable to even higher energies. So I told you about proton-proton 100 TeV, lepton-lepton 10 TeV, and especially if you're less familiar with this topic, you might wonder, okay, so isn't 100 just better than 10? And unfortunately, the answer is actually slightly more complicated. And so I wanted to just give you a feeling of a little bit how these two compare. And the main difference, but the bottom line is that protons involve the scattering constituents, so partons, and leptons at first order, sort of, they use the full center of mass energy available in the collisions. And now these two plots sort of give you sort of a feeling for signal and backgrounds, how these two also compare. So in terms of signal, you can actually try to do a bit more quantitative than these sort of qualitative statements, trying to think about some specific class of processes. This is an example for 2-to-2 processes. And then you can compare sort of what is the reach of producing the same number of signal events for a given center of mass energy in a proton-proton collision. Here I have highlighted 100 TeV. And for a lepton-lepton collider, here is an example for muon, but the electron is the same thing. And you can see that depending on sort of the initial state, gluon, quark, or the partonic cross-section is different to produce a final state from E plus E minus, mu plus mu minus, or proton-proton. So depending on various assumption, a 100 TeV proton-proton collider can produce a similar number of signal events of a few TeV to 20 TeV mu plus mu minus collider. But signal is one thing, but then it's also backgrounds. And here sort of lepton collider excel in terms of like low physics background. You can see here an example of sort of the cross-section for producing a Higgs over the total cross-section. And in lepton colliders, this is actually a pretty good starting point. While in proton-proton collision, you actually start from a very strong production of multi-jet background. So where strong production, strong interaction dominates. And so you pay a little bit of a price here, yeah, you pay a little bit price here with you need to sort of bridge this gap of a few order magnitude in backgrounds. Now, the reality is more complicated than these two plots aim to show. And practically, there are a lot of details that go beyond this simplified picture. And that's why in the report, we actually go in detail into several different physics scales because there are more nuisances coming into play. But the other aspect I wanted to highlight is that going to the current energy to this future multi-TeV collider is not a simple jump of energy. There are qualitative new challenges and qualitative new features that emerge. And I just wanted to give you a couple of brief examples. One is, I find it very interesting, which is when you go to this energy, this sort of simplified picture in which we think about two elementary particles interacting in an S-channel type of production. This is a cross-section that essentially goes down as 1 over S, where S is the square of the center of mass energy. At very high, at multi-TeV regime, actually different production mechanisms they become dominant at the scale with the logarithm of S, in which these colliders essentially become colliders of electroweak bosons, either W or Z. And so here you can see a plot just showing its function of a center of mass energy, just a production cross-section of a bunch of different processes that involve different final state. But the whole point that I'm trying to say is that the main production mechanisms qualitatively change going into these regimes. The second thing I wanted to highlight is that also on the detector side, we have qualitative new challenges. Only briefly, I picked only two. Radiation hardness is a big concern. It can be as high as 10 times the luminosity and requires strong R&D, which is very interesting. And the event reconstruction itself in the detector is quite a challenge and requires developing innovative algorithms, detector layouts. And one, I think, unifying requirement that is coming out from these studies is the need of accurate timing information. And I picked just one example since this was pretty new for SNOMAS. This is an example of a tracking detector in a muon collider detector. And all these gray line are charged particles from this beam-induced background. And for the first time during SNOMAS, it was shown that it is feasible using full simulation, detailed simulation studies to actually extract the needed physics information out of these events. Okay, but the obvious other question is, when can we get there? And here I copy-pasted sort of a table that has been worked out by an impressive amount of work at the Accelerator frontier in this implementation task force. And the main takeaway that I want you to get away from this is that we are not building these colliders tomorrow. They have significant challenges, and therefore it is critical that we sort of, if we want to go in this direction, it's critical that we address them as quickly as possible to move down this road. Okay, but the prize, the reward, if we manage to do that, is actually quite large. And I wanted to give you a few examples of that. And to do that, I like to classify usually the physics beyond standard model we are hunting in three categories. There is, we know there is some physics beyond standard model that we know of in the sense that we have observed phenomena that we are lacking in a fundamental explanation. The primary example of that is dark matter, but also matter-antimatter asymmetry, origin of neutrino masses are all good examples. We have a second class, which is guiding theoretical principle. We have theoretical principles that tell us that it's very likely that new physics is coming up at these energy scales. And I will try to give you an example of that. But we essentially heard about it already in Sally's talk about, for instance, naturalness. And finally, last but absolutely not least, I think historically we have seen that sort of we should be prepared to accept unexpected new phenomena that might come in, and they can really sort of revolutionize a little bit our understanding of the physics that lies, the physics that lies in nature. So let me start with an example on dark matter, and here what I really want to say in this slide is that dark matter has been observed gravitationally, and there is in the simplest possible models there are different ways that dark matter can be searched for in colliders. One of the most famous paradigms, I would say, is dark matter that is a weakly interacting massive particle. But you can also search for dark matter through a mediator that couples to dark matter, or there are many new ideas that are coming up that are beyond this weakly interacting massive particle paradigm. But just an example for these WIMP in minimal models, this is a quite attractive benchmark because given the measured density of dark matter, it can be very predictive in terms of telling us what is the target dark matter mass, because it basically can be fixed given the observed density and the type of representation where your dark matter lives. So this basically gives us a target, and that's what we try to illustrate in this summary plot. So this shows for different future collider as function of the mass of the dark matter target, the dark matter candidate, the reach of these colliders. And here you can see in red what I refer to as this thermal target. And so the target for the dark matter mass, once you fix its representation, if you want the theory underlying it. And here I've chosen one of the sort of more simplest and therefore, in my opinion, very compelling one. The different colors correspond to different type of searches. And just to give you a flavor, the blue color corresponds basically to situation where we produce dark matter through the interaction standard model particle that comes undetected in the detector, but then is detected through the recoil of some other visible particle. And this is a very model independent way to search for dark matter collider. But you can do a little bit better if you do slightly few assumptions and you think that sort of this dark matter is likely to be part to a more slightly bigger electroweak multiplet. And there you can look to the charge counterpart of this multiplet. And this can manifest with a macroscopic massive particle that travels through the detector. And the bottom line of this plot is that multi-TV collider are the machines that you need to reach this thermal target. So these are really sort of what we need to be able to answer this WIMP paradigm. I couldn't resist to tell you that I personally have a dream. And my dream starts with a direct detection experiment showing an axis in dark matter searches. And this dream continues with us at the LumiLSC finding maybe a charge counterpart of this multiplet that allows us to study these properties. And this finishes with a high energy collider, which then explores the whole spectrum of particles that comprise the theory behind it. I have to say I like realistic dreams, and I think this is one of them. But in addition to that, we can also look for more generally new physics in a new mediator, a new force that might manifest. And this is a very standard candle that we use to illustrate the power of future collider. This is a simple plot that shows the mass reach in a new mediator versus its coupling. And also nicely illustrated two different methods. So direct searches where you really look for a bump in a falling background spectrum versus indirect searches that allow you to go beyond the direct center of mass energy. And this is sensitive to essentially distribution in tails or angular distributions. And the point here is that future collider can really extend the high luminosity reach by order of magnitudes. By several orders of magnitude. So you can see here FCCHH as an example, multi-TV lepton collider and multi-TV muon colliders. I've told you up to so far about the power of extending the energy reach, but the other thing I want to point out is that high energy multi-TV collider can also be precision machines. And there is a lot of discussion in the report that shows you this with examples, but I just wanted to flash a few numbers. This is the Higgs factories that we heard about aim to produce about 1 million of Higgs in a very clean environment. Future high lepton collider aim to produce a similar order of magnitude, a slightly higher number of Higgs boson, and even a protoproton collider produces even more, albeit with a larger background. So these have the potential, if backgrounds can be controlled, to be also very high precision machine. And this is shown in detail in the report. We also heard about the importance of the quartic coupling of the trilinear and quartic coupling of the Higgs and the form of the Higgs potential. And just to highlight again that multi-TV collider are the machine that you need if you want to reach a precision of a few percent in this type of couplings. We also heard a little bit about naturalness, so I will not repeat the argument, but my point is that multi-TV collider are the machine that you need to really stress this test, stress these arguments, and improve them by a couple of orders of magnitude. And there are several ways you can resolve this guiding principle, this naturalness conundrum, if you want. I wanted just to mention a couple. One is for compositeness, meaning like the Higgs is not an elementary particle. And the other one is basically adding an extra contribution that cancels some of the divergences that happen at this level. And this is just an example of composite Higgs reach in future multi-TV collider as function of the mass of the compositeness and coupling. And again, the only point I want to say is that future collider gets to the multi-tens of TeV scale, which is one beyond the 10 TeV I was mentioning above, through a set of direct and indirect constraints. Finally, before concluding, I couldn't not mention supersymmetry, because this is really a theory that has the possibility to both alleviate the hierarchy problem, as I quickly mentioned, can provide a natural dark matter candidate, as well as is present in essentially every fundamental extension of the standard model that unify all forces, including gravity. And there are several ways to approach this problem, because supersymmetry has a large parameter space. You can look at simplified classes of signatures, or you can look at full models with additional assumption. Just to give you an example, since I talked briefly about stops and I've talked about electroweak kinons, these are example plots that we have in the report that shows you the reach for multi-TV collider for stop and electroweak partners or supersymmetric partners, compared to these black lines that show the LHC limits. And then one nice thing of this plot that shows also the complementarity, the different strength of different type of feature collider. For color particle, hadron collider are absolutely the best in probably the higher energy scale, getting to the 10 TeV scale. But for non-colored particle, lepton colliders are by far the best probe for higher masses. Okay, so I couldn't cover, of course, all the use cases that we have in the report, but I wanted to say that there is much, much more. So if you haven't seen your favorite topic, I invite you to have a look at the report. We have things like axion-like particle, heavy neutral lepton, dark photons, and more, all connected to the big fundamental questions that we talked about. And then in addition, we, of course, the colliders offer the flexibility to react and to study the fundamental physics if we get any hint of new physics from low energy experiments. And here I mentioned just two, like lepton flavor universality, hints of the lepton flavor universality violation from flavor physics, and the recent muon anomalous magnetic moment results. So let me go towards the conclusion, actually going a little bit back to the first day of the conference, where Joanne showed this picture and with very inspiring words, told us to have a campfire together, look at the sky, and look at our vision. And I hope she will allow me to just push this analogy slightly further. And this is the sky, not through my eyes, but through the James Webb eyes, which are much better than mine. Oops, sorry. Much better than mine, and both James Webb as well as us need a standard candle, and for us is the standard model of particle physics, and all around we have plenty of possibilities that are very exciting. And I will finish pushing this still one step further to say that when the morning comes and snow must end, it's equally important that we find the resources to develop the tools that get us to those stars. And that's why the Energy Frontier advocates for a very wide range and strong R&D activities that span accelerator, computing, instrumentation, theory, and all their intersection that will make this multi-TV collider a reality, and that is flexible enough to adapt to what we will or will not find along the way. Thank you.
Thank you, Simone, for summarizing such a broad topic in such a clear set of words and images. So we have questions. I think we can both ask questions directly to Simone, or just invite Sally to come back to the podium again, and you can now open the session to questions from everybody on both talks. And as far as I looked at the last time, there was nothing on the dock. So something, okay, good. So we take also a question and comments. So I see a hand raised there and there.
Hi, thanks for both the very nice talks. One question for Sally is that on the Higgs coupling summary where you gave all of the different collider options and different ones, I mean, the zeroth order takeaway was that they all had roughly the same precision. that it was, but there were a few places where that was not, didn't appear to be the case, but I could not squint and see what it was. I was wondering if you could comment on that.
Well, it was intentional that I didn't make the legend readable. There are differences because that's a logarithmic scale. So if you stare hard, you'll see that some machines do slightly better here, some do slightly better there. But the takeaway is that they're all, you know, much, much better than the high Lumi LHC that they're in advance. So they're not all the same, but the differences I would claim are minor. And the label is in the report.
So I'll take one from the Google Docs, which is from Sridhar Dasu saying, it's a question for Sally. What is the time scale in which a Higgs factory is interesting to build?
What is a time scale? I think it's always interesting because there's always a progression from high Lumi LHC to the Higgs factory. I don't see a scenario where it wouldn't be interesting.
So this is a question for Simone. What determines the scale of 100 TeV? Is this the, I don't think you addressed that.
Yeah, so I would say there are a couple of different things. So one is general exploration in terms of sort of what is technically feasible to get there. And the second part that I was trying to highlight is like that we have hints in terms of like naturalness, in terms of WIMP target that put us to this partonic 10 TeV energy scale. And those are nicely probed by either a 100 TeV collider or a 10 TeV hadron collider or a 10 TeV lepton collider. So those are sort of what we need to probe this scale from these arguments. As I think Sally nicely explained, those are not the same no-lose theorem that we had sort of for the Higgs, but I think are still very good hints in terms of like what is the natural target. And generally speaking, whenever you sort of try to push boundaries, I feel like the order of magnitude is usually the right amount of at least what you would do better. So I think those in both cases push our boundaries in the example I showed you by at least an order of magnitude.
Thank you.
This may be a difficult question. So given that HLLHC plus a Higgs factory feels like a 30-year program ahead of us, what is the key R&D on instrumentation and accelerator physics in the next decade for something that's 30 or 40 years out?
So the audio is terrible from here, but I think I got most of the question. I think you were asking what is the key R&D in terms of accelerator for the next decade?
For the next decade, given that these machines are probably 30 years away.
Yeah. So I don't want to speak too much about for the accelerator frontier because they have been working out sort of what are the key challenges. So actually there is a report for both, there is an accelerator frontier report that details sort of the challenges, the key R&D challenges for each type of these colliders. And each of them has different challenges, okay? From an experimental point of view, from sort of an energy frontier point of view, my view is simply we should try to get there and try to get there as fast as possible. Now, which priorities are there, I think is what the accelerator frontier should be set. I don't want to overspeak that. I don't know if someone from the accelerator frontier wants to summarize briefly what's their conclusions. No, they say no. So I think you can follow up with them over coffee on that part. But I think, you know, I showed you 3 types of colliders for the multi-TeV range, and each of them has very well-defined set of milestones for the next 10 years. That's, I think, is a very true statement.
There's one, Michael has one.
Oh, was it the detector or accelerator? Sorry. Both. Okay. Oh, I can tell you more about detectors. How much time do you have? No, I think I highlighted timing because I think is something that came across colliders as a big requirement for future colliders, having capabilities of accurate timing throughout the different subsystem of colliders. Then there are specific requirements that change depending on the type of collider. Hadron-Hadron collider, they have the need of extreme radiation hardness, which is a very interesting topic of research. E plus, E minus, especially for Higgs type of factory, they really need to go to low mass, for instance, low mass structure to allow it to go as low in momentum as possible and to get the most accurate measurements as possible. And yeah, there are several more, but I would say these are the kind of type of thing. Oh, the other one I think I like a lot to highlight is that I think in many of these situations, there is the need of real-time processing of data and decision-making. So I think there has been a tremendous, if I look like in the last 10 years, there has been a tremendous amount of progress there. And I think we need to keep going in that direction. That's another key element. And I'm sure people from the instrumentation frontier will be able to highlight many more. So these are things that I can highlight just to give an example.
There is a question there.
So while he gets there, maybe the last clarification I want to say on the detector, though, that I have in mind, is that the nice thing I would say is that there is some minimal amount of requirements for detector, and I don't think those are that far. And then there is sort of a wish list of things that you would like to get. And the more you get, the more physics you get out of it. That we should always remember, I think is an important point.
So I don't know if you can hear me from there. I saw also this morning, but also in the afternoon, several projections for the trilinear Higgs coupling, but I didn't see anything about the quadrilinear, while we know that there are projections for FCCHH and also in particular for the multi-TV, in particular multi-TV muon collider. So is it relevant, or how much is relevant for the future, and how can be inserted in this picture that you gave?
It's certainly relevant, and we'd very much like to measure the quartic coupling of the Higgs. I think the studies are very, very preliminary. There have been initial studies for a 10 TeV muon collider and for a 100 TeV hadron collider, and it's clear that you need the high energy to do them. But I don't think we have the final word yet. So it's just in its infancy, these studies.
There are a few hands there. Oh, there is a microphone also there.
Michael's been trying.
Yes, I wanted to give not a question, but an answer. I think this question of why one wants to go to 100 TeV or the 10 TeV parton scale is very important. And I think Simona gave one answer, which is that just this is the next step in exploration. But there are specific model answers that one can give to this question. Let me give a few of them. One of them is that it is a mystery to many of us why we didn't discover new physics at the LHC. And this is the question of why the new particles are so far above the Higgs mass. There are specific model building answers to that question, which go under the name of Dirac-Gay-Genos, little Higgs, models of composite Higgs, etc. Those models have their important physics in the tens of TeV energy region. And to test them, we have to go there. There's the question of flavor. Flavor has to be highly constrained if it has BSM effects in the TeV region. In the 10 TeV region, those constraints go away. And so that's the place to look for explanations of flavor. And finally, for dark matter, we talk a lot about light dark matter, which is weakly coupled, but we can also talk about dark matter, which is strongly coupled, which then has to be heavy. And again, that points to the tens of TeV region. Of course, I say tens of TeV, it would be nice to have a number, but for that, I think we need more experimental evidence to pin that down further. But I hope this explanation is useful to you in understanding why we really want to go to this general energy region. Okay, excuse me that that's not a question, but I hope it's informative.
This is for Simone. When you talked about linear colliders, there was a little bit of information on the Wakefield linear collider. Maybe I was distracted during the accelerator talk and should have asked then, but the luminosity seemed pretty spectacular. Is that based on a study or is that a guess, a forecast? What's that based on? I think it was slide 15 or 16.
So I can give, so actually that, yeah, I can give you my answer, but then I also invite someone from the Accelerator frontier to speak up easily. So I'll give you my understanding.
Could you show the slide so people see the number?
Maybe. There we go. This slide here, I assume you mean. So I really invite you to look and at the implementation task force report. They've done a very nice job at trying to illustrate that. The one has to be a little bit careful because there are essentially various options for moving forward with Wakefield acceleration techniques towards a real design of a collider. And this option can differ very drastically in terms of like luminosity, the interplay between luminosity, power consumption, and actually if you want positrons, so do you want to have a plus and minus collision versus you want to have photon-photon collisions, okay? You can have very spectacular luminosity at very high energies, but usually you pay a price in power consumption unless we have new ideas. You can lower the power consumption and then you pay a price in luminosity. You can go to gamma-gamma and it's much easier and requires lower R&D time, but then you pay a price in physics because it's not as powerful as the plus and minus. So there are all these sort of different levels, and that's what I'm trying to say here, that sort of, I think it would be very beneficial to study way more detail, for instance, the photon-photon case than we had time so far. But yeah, the high luminosity, I would say, is not a given, and there are various compromises that one will have to make. So yeah, that's my take to it. If anyone from the accelerator wants to add more.
So I would like to add to that from the Accelerator Frontier that the ITF, we hope, was a very useful process, but the ITF itself did not evaluate the feasibility of luminosity. We tried to evaluate the cost, but we took the luminosities given to us by the proponents. And I should also note that in the discussions that we've had here with the various members of the Wakefield Collider program, there are some questions about whether they're fully self-consistent. There's some questions as to whether the parameter sets are fully self-consistent at this time. And so I think there's going to be working through there and understanding these luminosities in a little bit more detail.
We have a question up there.
Yes, I'm Eric Essery from Berkeley Lab, and I work on Wakefield accelerators. Is this on? Okay. In a nutshell, I mean, it's a very long story. What we've been concentrating on in our community is the physics of the LINAC. This is a new technology. Wakefield's based on plasmas or event structures. But the bottom line is we have a good idea for how much charge we can accelerate based on simulations, theory, and experiments. We have an idea how we get to high energies by building 10 GeV stages, coupling those together. And the other key thing for luminosity is rep rate. And for Wakefield accelerators, we need to go to high rep rate, tens of kilohertz. And for laser drivers, for example, we're now at the few hertz level. So there's a big jump in laser technology, but there are laser technologies emerging that promise these high rep rates. In particular, my favorite is fiber lasers, the coherent combining fibers, and that's making very fast progress, and intrinsically operates at very high efficiencies and high rep rates. So there is promise, but again, it's, there's a long way to go.
Yeah, thank you. Excellent talks. Given the renewed interest in muon colliders, it seems to me that it's absolutely imperative that we can actually demonstrate you can do precision physics in the environment with that incredible background, particularly in the forward region where everything is just flooded with electrons. I mean, that was a previous criticism of the previous muon acceleration program. Could you comment on the work that's going into actually really demonstrating with full simulations that you can do the physics in that environment? Because it's clearly one of the challenges, and what impact precision timing might have on that.
Yeah. So yeah, I can comment on especially the work on sort of the detector side on the extracting physics information about that. And this is, in fact, I try to sort of highlight a little bit because I think it's new for it is new for this no mass free part. But essentially, for the first time, there were full simulation based on let's say accelerator simulation of the beam, starting from 100 meters away. You simulate your muon decays, your halo electrons, and so on, and then you take these four vectors and you literally propagate through a full giant force simulation of your detector. And the detector has been used is a Stroman detector, starting from a detailed simulation of the click detector and modified for the muon collider environment. But it's a full detailed simulation. And then the deposit of energy get digitized as we do in normal collider simulations into electric signals. And then those get reconstructed through algorithms. So we run the full chain. And there was a very nice couple of white papers submitted that describes the full chain and showed that a whole range of performance going from charged particle reconstruction in very reasonable time in minutes or seconds per event, not days, and calorimeter reconstruction, efficiency resolution, separation between hadronically decay Higgs and hadronically decay Z, which is critical, and the muon collider and muon reconstruction. The current acceptance is limited to about 10 degrees due to shielding. But one of the work that I think needs to happen going forward is a re-optimization of the shielding that was sort of put together actually from the previous NOMAS report in 2013, and especially going to higher energies and clear how that is not optimized. And maybe the last, this I would say is a good summary of the situation. So it's a pretty, starts to be a pretty robust now look into the feasibility.
So this one, okay, so do you want to read it?
Yeah, so from the Google Docs, there is a follow-up for Sally, or I guess I'm going to take it too. If a high energy, high luminosity lepton collider CDR is available in 2 decades, we could do the precision Higgs and search for new physics associated with any discrepancies found in one machine. We do not need a Higgs factory then at 250, right?
I didn't understand your question.
It's basically saying, it's basically saying.
I did not, actually, I couldn't hear it.
I think Simone got it too.
If you want, I can attempt and then you can jump in. We were just to repeat, the question is essentially if in about 2 decades, one has the technology to build a multi-TV collider, it appears that those colliders have the capability also to perform accurate measurement of Higgs coupling. And then the question is that if you haven't built yet Higgs factory, would make sense to go directly to a multi-TV collider program. I would say my first answer is that we hope that by the time we have a Higgs factory up and running, that would be my first thing. But it's correct, and it's one point that I was trying to highlight, that these multi-TV machines can also be precision machines. Now, these Higgs factory are really tailored not only to be precision machine on the Higgs, but as Sally correctly pointed out towards the end, they have unique BSM capabilities to lower coupling. So if we get to that point, I think in around 20 years, that's, I think, a discussion to have on what direction one want to go. I might have my preference, but I think it's a discussion that there is no point in settling right now.
Yeah, let me just add to that. The E+ E- machines have a broad program beyond the Higgs couplings. So although Higgs couplings are similar in the projections for the high energy muon collider and the E+ E- machines, the E+ E- machines have the capabilities to change their energy and so have a different range of standard model physics beyond just BSM and so forth. At the Z-pole, they can do exquisitely precise measurements, W pair production of anomalous couplings. So the physics menu is different. So as Simona said, that's a discussion that we could productively have at the time.
There is a question up in the gallery. Oh, hi, Carlos.
You got to shout. Carlos, we know you can
Yes,
shout.
You can.
We will repeat it.
No, we can hear you.
We will repeat it here.
We will repeat it. We will repeat it. Shout.
Okay, I have a question. So then imagine that we have a discovery that I think is a very concrete possibility. In what sense such a discovery can shape the future of life?
The question was, suppose we discover, I presume you mean some new particle at the high Lumi LHC. Well, first we have the big party. It's wonderful. And then we reevaluate what that means in light of the E+ E- machines and the muon collider. So that would be a wonderful problem to have. Yeah.
Okay. I just want, well, thanks for the question, because I think it's one of the points I try to highlight in the talk that different multi-TV, for instance, collider options have different strengths. One can go on for hours, days, or months discussing a priori across with loose priors which one is the best. But such a discovery, either coming in the LHC or coming from a low energy experiment, can actually be, I would say, a decisive factor in immediately guiding us on where we want to go. And this is why I think it is absolutely of paramount importance to maintain a very broad R&D program, not to narrow it down and go all for one option now, but being flexible. That's why flexibility, I try to highlight it more, because this can really shape our decision for the future.
So do we have more questions from the audience? We don't have anything in the Google Doc, right? No, not at the moment. If I don't see anything else, given that we are right at 3:30, probably we can close here. And thank our speakers again, and thank all the participants.